All right, so we'll keep going with domain. So again, every time for domain, just ask yourself those same 3 questions. Are there any rules that are being violated? Is there a denominator that shouldn't be 0? Is there an even root that should always be positive? Is there a logarithm that should always be positive? So if I look at letter E, there is no denominator, there is no even root, there is no logarithm. So by default, the domain is all real numbers, slam dunk. By the way, what's the shape of that? It's an absolute value. What does that look like? It's a V. Yeah, looks like this. Okay. All right, next one. E to the x plus 7. We call that an exponential. Does it have any of the big 3? Does it have a denominator? Does it have an even root? Does it have a logarithm? So what's the domain? All real numbers. Okay? Just ask yourself the big 3. And what all real numbers means is that that function welcomes in any kind of number possible. Okay, there's no number that can't be used in either of those 2 functions. All right, so now we want to talk about range. All right, the range of a function is its set of viable y values from low to high. Okay, how much will that stretch? Will it go on infinitum? Okay, as far high and as far low as you can go, or are there boundaries to that? And so I feel like it's most easily that we think of these using a graph. But in order to do a graph, without a graphing calculator, you got to be semi-decent at knowing what graphs look like. Okay, knowing what graphs look like mean there are some graphs that I reasonably expect that you have a general idea of what it looks like. So when I say absolute value, your brain thinks V. You don't have to have a perfect V all drawn perfectly. You just need to know that an absolute value makes a V graph. And when I say parabola or you see an x squared, that you can think of what a parabola looks like. And when I say logarithm, that you don't know exactly what the logarithm looks like, but you know that pretty much all logarithms start like this and then curve off sideways. That you have an idea. If I say sine, that you're like, oh yeah, this way. General idea, okay? Nobody's going to ask you to perfectly graph a sine graph. Nobody's going to ask you to perfectly graph it, but you have to have a general idea. So these are the ones you need to know, okay? Absolute value, you've got to know that that looks like a V. And you have to know if I throw a negative in front of it, what's that going to do to the V? Flip it upside down. Okay, good idea. Squares. You need to know that squares are going to look like this, or again, if they have a negative, they would look like that. I'm not going to judge your square graph on whether it's the right skinniness or the right width. I'm just going to judge, is it facing the right direction? Do you have it going up? Do you have it going down? Okay, square roots. That's the inverse, okay? This whole column here are the inverses. So if you have a square, you have to have a square root. A square root is half a parabola that goes off towards the side. Starts at the origin, it's only half of it, top half. How could it be the bottom half? What would it need to have in front of it? It would need to have a negative. Still would start at the origin, but then it's gonna head off on the lower part. Okay, anybody know what a cube looks like, just in general? Okay, just a snake sort of thing. Okay, a pinwheel or something, so it's like this. Okay, it goes to the origin too. All these things start out going through the origin, that's the nice part. Okay. So a cube root. Okay, so do you see how the arrows on the cube, one is going up and one is going down? For a cube root, the arrows, one is going left, one is going right. And so it looks like this. Okay, it has a similar shape to it, but it's more horizontal than vertical. Okay, an inverse graph. This is one people are less familiar with. An inverse graph, go ahead and just like use, it has asymptotes. So use a different color or something to make some asymptotes. An inverse graph looks like this. It's got a section in quadrant 1 and a section in quadrant 3. There's another name for that. Does anybody know the other name? Starts with a high. Has a purr in it. Ends with a bola. Yeah, that's another name for it. Some people call that a hyperbola. The official name for it is an inverse. It's always in quadrants 1 and 3 with asymptotes there. What's the only way to flip it to quadrants 2 and 4? Throw a negative in front of it. Okay, then you flipped it to quadrants 2 and 4. A square inverse. That also has asymptotes. But when you square something, what does it do to numbers that are already positive? Keeps them positive. What does it do to numbers that are negative? Makes them positive. So what does it do to the graph? If it's already positive, it keeps it positive. If it's negative, it makes it positive. This is a square inverse graph. All right, so what does an equation for that look like? I know you guys know what absolute value looks like with the bars. I know you'll know what squares and cubes look like. The formulas for inverses are 1 over x, it's a fraction. And the formula for square inverses is 1 over x squared. Okay, so they are have asymptotes, where they are pieces that are broken by the y-axis and the x bounded by the y-axis and the x-axis. So you should generally know what that looks like. Okay, a 5 over x is going to look the same. I am not going to judge the difference if you graph a 1 over x, a 2 over x, a 3 over x, whatever, a 10 over x, a 17 over x. I'm not going to the naked eye, they're all going to look the same. Okay? Now, the graphing calculator would tell you there's slight differences in the decimal values on those graphs, but for us, for what we're doing, you just need to know that it looks like that in quadrants 1 and 3. The only way to switch it to quadrants 2 and 4 would be to put negative in front of it, okay? Again, if there's a square in all of these, you need to know that it's not in 1 and 3 anymore, it's in 1 and 2, quadrants 1 and 2, the top. And the only way to flip them down to the opposite quadrants is to throw a negative in front of it. So generically, I could ask you, what quadrants is this graph in? I'm not maybe not ask you to graph it, just what quadrants will it be in? You got to tell me it's in quadrant 3 and 4 because it's a square and because it's negative. Okay, so I don't want you to get hung up on making perfect graphs, but the concept is what we're looking for. All right, any questions so far on the graphs you should know? Okay, last two. I have terrible, there we go, exponential. Okay, an exponential graph has an asymptote also. Its asymptote is the x-axis, and what the exponential does is it hugs the x-axis and then explodes up, always going through the number 1 on the y-axis. Okay, that is an exponential. Think of exponential like an explosion or that it gets excited. Okay, that graph just starts out super boring for a long time, and then as soon as it gets to the y-axis, it has that moment of explosion, and then it's just going to shoot straight up. A logarithm does the opposite. A logarithm has this excitement happening first. So a logarithm is really, really steep as it's approaching, but as soon as it gets to the x-axis and it hits the number 1, then it just sort of loses so I think of logarithms as losing their excitement. It starts with L. Logarithms lose excitement. They get lazy. And so the logarithm is just going to sort of peter out and just sort of like, I got too tired. I can't go anymore. Okay? But it always happens at the number 1 as well. So they have similar shapes, but their explosions happen at different times. Okay, so an exponential and a logarithm. Okay, any questions?
What's the exponential equation?
Oh, there's lots of them. You're probably most familiar with e to the x, but it could be the number e. Does anybody know what the number e is, by the way?
2, a little bit more than 2.
Quite a bit more than 2, actually. 2.7. 2.7. So it's actually closer to 3 than it is to 2, but it's 2.7. Okay, but that number is irrelevant. I mean, that's a special number. It occurs a lot in nature. But exponentials can be 5 to the x. They can be 11 to the x. They can be anything to the x would be an exponential. And logarithms, the most common is a natural logarithm. you know, but we can have logarithms of base, they just happen to have base e, but you can have lots of different logarithms too. But again, I'm not going to judge you on whether or not your explosion is an E explosion or a 5 explosion or a 10 explosion. I mean, well, all that means is that it gets steeper faster. What I'm going to judge is it going through the number 1 and is the explosion happening after that. I'm not going to judge whether you get the angle perfectly right. Okay? Good question. Thanks, Nathan. Okay. All right, so again, we've been talking about this already. If you want to make something go upside down, reflect over the x-axis, you're going to throw a negative on the outside or in front. Okay, that's what makes something, a parabola go upside down. It's what makes a absolute value go upside down. It will make a cubic go upside down. Any negative that you throw in front of that is going to make it go upside down. If you want to reflect it over the y-axis, you're going to have an inside negative. Okay? The best way for me to illustrate that for you, I feel like, is with a square root. So if you have a normal square root, it looks like this. Okay, that's a normal square root. If you throw a negative in front of it, so I'm going to use red. If I throw a negative in front of it on the outside, then it's going to make it go over the x-axis of the reflection, so it's going to be reflected upside down. If I throw a negative on the inside, it is going to reflect it over the y-axis, and instead of going upside down, it goes backwards, like that. So what if I do both? Then it's going to go upside down and backwards. Okay, so if I include both of them, let me see if I can do that. So if I have both of them at the same time, then I'm going to go upside down and backwards. Can you think of a graph where if you did put a negative on the inside, the graph would still look the same? Can you think of a graph where if you put the graph on the inside and flipped it over the y-axis, where the graph would look, you couldn't tell the difference? Parabola, sure. Yeah, if you have a parabola, okay, x squared, then that looks like this. If I throw a negative on the inside of that and I reflect it, then it still looks like this because nothing changed about it. Okay, can you think of any other one? There's another kind of famous one that does that too. Absolute value, yeah, absolute value is the same. Now, a negative on the outside of both of those does change it because they both go upside down. But if you flip an absolute value, it's still a v. If you flip a parabola, it's still a u. It hasn't changed anything. So I would expect that you could reasonably create the graph of those two equations for me. Okay, I would expect that you would understand, so let's look at the x squared, that you in your mind would go x squared, I can draw a parabola. The parabola is going up because it's a positive parabola. And then I would expect that you would be able to interpret what these two numbers do to the parabola. So originally, where does the parabola start? On what significant point of the graph?
Origin.
The origin. Once I've done the +2 and the -3, do you remember what that does to the parabola?
It moves the origin.
It does move it, but in what direction? What about the +2?
Left, down, 3 to the left.
No, it goes to the left. Did you say down 2 to the left?
That's down 3.
Yes, okay, so the +2 actually means left. The down 3, then the -3 means down. And so I would expect that on a grid, turn your notability paper into grid or pull some of the grids in that I've done for you, that you would be able to go left 2, down 3, throw an upwards parabola on there. I am not going to judge if your parabola is skinny enough or fat enough. I'm going to judge, is your vertex in the right spot and it is at least opening in the right direction. Those are the two things I'm going to do. Because from that, you can easily tell what the range is. Okay, so let's talk about that. The domain is all real numbers. Because no denominator, no even root, no log. The range is done visually. The range picks the lowest value and then goes up from there. So my range is going to be -3, and y has to be all the numbers greater than that. That -3 would be the lowest it could go, and all y values produced by this graph would be going up from that. So that would be how you produce that. Okay, I would also expect you could do the same thing for the other equation, for the absolute value, that you see it and you think v on the origin. And then that you look at the -5 and the +2, and you think, I can take that v and I can move it in what direction? Okay, so let's try that. In what direction? Aiden, what do you think?
Down, so I'm going to go, we go up 2 and then 5 to the right.
Great. Okay, so right 5, up 2. And so then you create for me on a grid, a good notability grid or something, that you're going to go 1, 2, 3, 4, 5, 1, 2, and you're going to go up from there. And then you're going to tell me the domain is all real numbers because there's no denominators, no even roots, and no logs. And the range is going to be 2, and all the y's are going to be greater than that. Now you might notice that the book would also use interval notation. So interval notation would be -3 bracket, comma, positive infinity. That's the same thing. That means -3 is the lowest and infinity is the highest. For the other one, it would be 2 is the lowest and infinity is the highest. That's another way to write that. I accept either. You'll see me more commonly use inequality notation, but I do not mind. The thing I don't like about interval notation, I really don't like interval notation when it's something like this. Okay. Because out of context, what could that look like? It could look like the 0.25. Is it the 0.25 or is it the interval from 2 to 5? So that's why I use inequality notation. I prefer it because it's less ambiguous. This is ambiguous unless you know the context of the question. But just so that you understand, 2 to 5 with parentheses would be this. It would be 2 to 5 open-ended. It would not include 2 or 5. You have to have a bracket to include it. So another way to write that would be like this, 2 to 5 without the lines underneath it. Okay, I prefer inequality notation. All right, any questions on that so far? Okay, so then you get to some of you I saw were using your digital graph paper already. So in the module for handouts, you'll have this. You may use an entire digital one. You can use your notability to just circle 1 and pull 1 into your homework and just paste 1 graph, or you can turn your whole paper into graph paper. It doesn't matter to me. But please use some kind of a grid. We can skip that one. Okay, last thing. And then I'm going to give you the rest of the time to work. Got a half an hour. Okay, last thing we're going to do is I'm going to just refresh your algebra on some things that I would expect you to be able to do as well. Okay, so notice we're focusing not on our calculator. We're focusing on graphing without our calculator. And I'd like you to be able to solve this without your calculator. I do not expect a decimal an answer. I expect an algebraic answer. All right, so as we work on this, I'm curious if you have a starting spot for me. If we were to solve that, in other words, get x by itself, do you remember from probably first semester last year how to solve this? Oh, so beautiful. Good job. Way to go, Luke. Okay, what kind of an equation is this? So Nathan asked about this earlier. Since the x is kind of up there, what's the name of this equation? Exponential. So when you're solving something, you always want to do the inverse. So if you're like, okay, it was an exponential. What did we talk about again when we were doing? Oh, exponentials and logarithms are the inverse of each other. So if the problem is an exponential, you're going to do a logarithm. The only logarithm you will ever need in this class is the natural logarithm. Please don't use any other one. Okay? The only one you will need in here is natural log. So we are going to natural log on both sides of the problem. So that means I'm going to throw an ln in front of the parentheses, 2.018 x to the negative 1. And I'm going to include an ln in front of parentheses on the other side. So parentheses are part of your good format. So in an English class, you use periods, you use semicolons, you use correct grammar. In math, we use correct grammar, especially in this class. All right, what happens when you use a logarithm is something fun happens to this guy. When you use a logarithm, there's a property that says as soon as you put a logarithm on an exponential problem, you can move that. Do you remember where it goes? Yeah, it does. It's like, okay, that gets to pull out to the front. So now our problem becomes a new set of parentheses, x minus 1, multiplied by the 2.018. And on the other side, we still have the log. So my purpose is I am trying to get x by itself. So at least now I've moved x down into the forward part of the problem. What's next? Okay, divide. I don't have my calculator, but that's okay. I'm just going to write that I'm dividing. Okay. Now, lesser calculus students might tell me to cancel out the ln's at this point, but I know that you would never do that because that is illegal. You cannot divide the word logarithm. It's a word, okay? So that does not work. So this is the natural log of 3 divided by the natural log of 2.08. Just leave it like that. Okay, you don't have your calculator. I'm not expecting you to know how to do that. And then your final version of the answer would just be to add 1. So your answer is going to look like this. Okay, and that's all I want. Okay, so no calculator, just giving me the algebraic answer for it. All right, we have one more to solve algebraically. Any final questions on that? All right, here's your last one. Okay. Now something about this is similar to our last one. What kind of equation is this? It is exponential, but how many exponentials are there? 2. Last time, what did we do? Use the log. Well, let me show you the other illegal thing. So sometimes you're like, well, hey, I used a log last time, a natural log. I'm going to use it again, and I'm going to do this. I'm going to do ln around 5 to the x, and I'm going to do an ln around 5 to the negative x, and I'm going to do an ln around 3. Unfortunately, that's illegal too. Okay, there's so many things that look so good, but are illegal in math. You can only have one logarithm on each side. You can't have 2 logarithms on the same side. We need a different way to solve this. So logarithms don't work when you have 2 exponentials. All right, so that is no good. So I'm going to show you this amazing substitution trick to solve this. All right, here we go. We're going to make it not an exponential anymore. I'd like you to, and don't worry, I'm not going to expect you to come up with this on your own. I'm showing you how to do it so you know how to do it next time. Let's take out the logarithm and let's replace it with a random letter that I'm going to choose. I'm going to choose A. So every time I see this, I'm going to replace it. So that means I'm going to replace this with A. What do I replace the other one with? Not negative A. A to the negative 1. Okay, that would be the equivalent of that, equals 3. But Matthew, I liked what you were thinking, because what is A to the negative 1? Okay, yeah. So this is now this problem. Okay, A plus 1 over A equals 3. So now I have one A in the numerator, and where's the other A? In the denominator, okay? What do I do when I have something that has a denominator? Well, I get common denominators. Okay, so how am I going to get a common denominator here? What needs the common denominator? This A first needs a common denominator. Okay, so technically, what's already the denominator of that A? Okay, so technically this denominator, bless you, is already 1. So if it's already 1, how do I make it common to the other one, to the other denominator? What does it need? It needs an a, so I'm going to give it an a. But if I give the denominator an a, what else do I have to do? Give the numerator an a. So now what does the numerator become? Okay, so I have a squared plus 1, which is the other numerator, and they share the common denominator a. So I have common denominator. On the other side, I have a 3, but what's its denominator? This is the third time you've seen that today. Isn't that, I mean, it's amazing how your brain, just as soon as you put 3 over 1, something about your brain hopefully goes, oh, cross multiply. And so I am going to cross multiply. So I'm going to get a squared plus 1 equals 3a. This problem started out as an exponential problem. What kind of a problem is it now? It started as an exponential, 5 to the x. What did it turn into? What do you call something that has a square in it? Well, its graph is a parabola. It's called a quadratic. And how do you solve a quadratic? Not all quadratics factor. This one doesn't. The quadratic formula. But what does the quadratic formula need before you can use it? It needs an a and a b and a c, and what has to be on the opposite side? A 0. And so this is not quite ready. How do I make this equal to 0? Subtract 3a. So I'm going to have a squared minus 3a plus 1 equals 0. This is now a quadratic, and I can use the quadratic formula. All right, so the quadratic formula says the answer is, okay, do you remember quadratic math? X equals negative b plus or minus the square root. B squared minus 4ac all over 2a. So we've got this. If you don't jot this down, because you're going to, here's your quadratic formula. So what's in the negative b position? It's negative 3. So if I have negative 3, I'm going to have positive 3. Plus or minus. What's in the b squared position? 9 minus 4 times, what's in the, the a is the value of the coefficient, right? That's kind of confusing. The a's in the quadratic formula are not the same thing as the letter a I'm using as my variable, okay? Because what's in front of this a squared right here? 1. Okay, so that's what I'm using in my quadratic formula. So 4 times 1 times 1, all over 2 times 1. So we have a equals 3 plus or minus the square root of 5 over 2. Everybody get the same thing for your quadratic formula? Is that the answer to my problem? What's that the answer for? A. But what does A stand for? Okay, so I got to change it back. Okay, A stands for 5 to the x. So it's, and what do I need to find the answer for? The question at the beginning said solve. And solve for what? X. So now that I've replaced it back, so I did a whole timeout thing, and now I'm going to replace it back. How do I get my x? So what type of problem did I just change it back into? I changed it back into an exponential. So how do I solve my now single exponential? So it was a double exponential at the beginning. Now I'm a single exponential, and I'm allowed to use a logarithm. And so I will use my logarithm on both sides. So I will have the logarithm of 5 to the x and the logarithm of 3 plus or minus the square root of 5 over 2, all in parentheses. Only one logarithm on each side, not separate logarithms for every number. One logarithm on each side. And the x can go where? To the front. And how do I get x by itself? Divide by the logarithm. So I have one logarithm in the numerator and I have one logarithm in the denominator. Those logarithms do not cancel or reduce each other out. That is the algebraic answer to that problem. This is the kind of problem you feel really good when you get done. You're like, wow, that was worthwhile. I worked my brain, and I did lots of legal and math magic here to have that all happen.